Two types. This is the screencast for the Chapter 20 homework that was due on September 27th. I guess it's 26. Oops, sorry about that. Anyhow, problem 7. So if it basically said that you had 1 times 10 to the 12th extra electrons, and they were split among 2 spheres. So each of those spheres got half of that. That's 5 times 10 to the 11th extra electrons. So to find the charge on each sphere, you take that electron, multiply it by the charge per 1 electron, which is something you should know or be able to get off of your formula sheet. And that equals 8 times 10 to the negative 8th coulombs, or negative 80 nanocoulombs. It's a negative because they're electrons. For problem 14, it's asking for the distance between 2 charges. So it gave you the 2 charges, gave you the force. So this is just an application of Coulomb's law. It came out to 2.57 centimeters or 0.0257 meters. For problem 24, you were given an electric field strength that bees could detect an electric field. And we're going to assume a bumblebee is a point source charge, which is a little funny because they're big. But the electric field formula from a point source is kq over r squared. So I rearranged that to solve for the radius or distance from the bee, and that was 0.06 meters or 6 centimeters. So yeah, a bee could detect another bee. It might just mean that if they were in adjacent flowers, they would know not to go back to the other one to pollinate it. It's kind of interesting. Problem 29 we went over in class. So unfortunately I did that on 2 pages. So here's the setup with the picture. And so where we get the electric field caused by each of the individual charges, and then the net electric field is going to the right. So we add up the horizontal parts, we cancel out the vertical parts. We need to use this as the distance, so that hypotenuse, to determine the electric field from each one. And it comes out to be about 2,500 newtons per coulomb overall. So sorry about that being split on both pages. You may want to go back and look at that. For problems 33 and 35, those deal with capacitors. The only formula for capacitance in this chapter was E equals Q, E sub 0, which is vacuum permittivity, over A. So the area of the capacitor was 4 centimeters on each side, so 0.04 meters squared, which is 0.0016 square meters. The charge, therefore, would equal this formula rearranged, and that's the charge per plate. So it asks for it in nanocoulombs, but I tend to like to give things in coulombs, so 1.4 times 10 to the negative 8th coulombs per plate. 35 we went over in class. I think the key thing there is thinking about the balance forces. The electric force and gravitational force need to equal each other. So the gravitational force I can find from the mass, which was 1 gram. So that's the gravitational force right there. And for the bee to be suspended, the upper plate had to be positive, lower plate negative. Set those equal, and I get the electric field strength in between these. Once I know the electric field strength and the area of the plates, then I can go and find the charge on either plate. I think the book answer was 1.63 times 10 to the 7th coulombs. It should be 10 to the negative 7th coulombs. For number 37, we went over that in class also. The idea is here towards this peak where the charges pile up, we get charges close to each other, and we also get a stronger electric field. For P51, we want to think both of Coulomb's law and Newton's second law. So in this particular case, we're looking at, I didn't draw a picture for this. Dang it. Maybe, it's giving an acceleration for an object with a known mass, which is 1 gram, and it gave the acceleration. So for 2 objects that were kind of accelerating away from each other, 2 little particles, I think. And this is for each one of them. So that tells us the electric force on each of the particles. To find the charge on each of the particles, we use Coulomb's law. Since the charges were identical, it was kq squared over the distance squared. Notice I'm using meters instead of centimeters, so I get that the charge on each sphere was 1 times 10 to the negative 7th coulombs. P68 went over this as well. The key thing here is there's a lot of different aspects. I think this is a better problem than maybe this earlier one with capacitors. I know that was kind of tough because of this formula with capacitance. But this down here is something that involves gravity and Coulomb's law. Those you should be very familiar with at this point. So, thinking about that, again, we use the triangle here and the mass. The mass would give us the gravitational force. That's the vertical component of the force on this, and equal in magnitude to the vertical component of the tension. And if we know the angle, and we know the vertical component of force, then we can figure out the electric force, which is the horizontal component, which I got over here. Then I can work back and use that electric force, knowing that these two charges have equal magnitude, and knowing the distance between them because I used trig for this 1 meter long string in a 20-degree angle. Can go back and then figure out what the charge is on each one. It's about 7.5 times 10 to the negative 7 coulombs. So I think that this free body diagram is the most important thing in terms of helping to solve the rest of this problem. So hopefully those are things that will make sense to you, and you'll be able to apply those problems on our next test.